So, good evening, everyone. And first, thank you very much to Renzo for organizing this amazing conference. But I want to add something to thank you very much to you all because this conference is amazing because you all made it amazing. Okay, so from the scientific point of view, but also from the human point of view. For me, that was the first time. It has been really a pleasure to be here. Thank you very much. Okay, so as has been said, the title is a bit weird respect to all the others, but I made all my efforts to show there is some topology inside and many connection with what I've seen also this afternoon. Okay, so let's start with the real goal of at least this work, which is the following. I consider a non-holonomic system, which is a mechanical system which has constraint in the velocities. The presence of the constraints in the velocities make the system not to be Hamiltonian. So this means that it is not variational, and in particular, we cannot apply Noether theorem that has been named many times. Okay, this is a problem, of course, in mechanics or in general in dynamics because we cannot obtain first integral or conserved quantities out of symmetries. But there are natural questions that in mechanics arise. And for example, this one, which is, given the symmetry of a non-holonomic system, is it possible to say a priori if this system is integrable in some sense that I will explain? The green one is related to the new part, which is related also to what I've seen here, and is, if this system is integral, which is the global structure of the phase space? And here, geometric phases plays a fundamental role. And since Noether theorem does not hold, one can say how to obtain first integral, because this is the key point. Is it possible somehow to extend Noether theorem outside the variational setup? Okay, so this is the plan. I will spend quite a lot of time here introducing and studying something which is really classical indeed, which is Liouville-Arnold theorem, but from a global point of view. Then I will try to extend this notion outside the Hamiltonian setup, and finally say something about integrability for non-holonomic systems. Okay, so this is Liouville-Arnold theorem, and says that if we have a symplectic manifold of dimension 2D and a map F, which is a surjective submersion, okay, such that the level set of this map are connected compact, and the component pairwise commute with respect to the Poisson structure of the manifold, then the fiber of the map F are diffeomorphic to tori of dimension D. But indeed, there is much more. The manifold D is a TD bundle, and the fibers are Lagrangian with respect to the symplectic form. But if we look a little bit more carefully, the let's say, local structure of this bundle is the one of a principal bundle, but just from a local point of view. And then if we can choose bundle coordinates that are symplectic. And with respect to these bundle coordinates that are symplectic, we can take the Hamiltonian vector field of every component here, and it turns out that it is quasi-periodic on the tori here, which means that it is conjugated to a linear flow of tori. So the situation is exactly this one. This is the local structure of the manifold M. Okay. Now, if one look a little bit more carefully at the proof of Liouville-Arnold theorem, can realize that there are three choices, three free choices, let's say, and they reflect already in the local structure of the change of coordinates. And the choices are, oh, sorry, I don't want to spoil something. The choices are here, the basis of the period lasses that arise when you consider a multi-flow action at the beginning of the proof. And then we have another choice, which is the zero when you want to count the angles, and finally a constant of integration when you compute the angles, the I variable. Of course, if we make another choice, nothing special happened. But from the global point of view of the geometry of the phase space, the difference is important. And let's see why. Well, because there are obstructions to extend the torus structure to the whole bundle. I mean, if one would like, sorry, let's say this way. If we want to see if the bundle, the manifold M is a product bundle, we have to face these two obstructions. This one, the so-called Chern-Daustermann class, is related to the choice of, or the existence, let's say, of a global section of the bundle. While this, which is here related to the choice of the generators of the lattice, which is called the monodromy, and is exactly the same obstruction or defect that we have seen in the talks of Garrett before, or the one of Random, some days ago. And now I will show why. Okay, I say that it is a torus bundle. I can figure it out like this. But there are points whose fibers are not regular tori. For example, in this case, the fiber over this point can be, or exactly is, what is called a pinch torus. And for example, this system is a nonlinear oscillator with a special potential, and the linear part is in resonance 1 minus 1. Okay, so it's the real, okay, a mechanical system. And in this case, one realized that if you take a basis for the homology of the tori and you go around the singularity, when you end up the same at the initial point, the base is different. Here there is a scheme that shows what happens. So when we end up here, indeed, the basis of the lattice is different. Okay? And we can see it as a monodromy representation of the action space on the automorphism of the homology of the torus. But it has other interpretations. For example, here I can see that this kind of systems has an exact symmetry. Usually it is the third component of the angular momentum, which is conserved, while the other symmetry, whose flow is the red one, is not exact. So when we do a turn, we end up at the same, let's say, Poincaré section, but not at the same point. So what is missing here is a kind of rotation angle that we have to compute, which is exactly a phase. Okay? And here it is something extremely interesting because it can be described in terms of a generator of the lattice, okay, of the period lattice, but indeed, in this special case, this is the quantum counterpart of the of the system. Let's say better, we consider a system with two degrees of freedom, and we quantize this in the way you prefer. And then the system is still integrable. And what you see, the point that you see here are the joint spectrum of the Hamiltonian and the angular momentum. And so what you can see is there is, or we can interpret as a defect in the spectrum of the corresponding system. One obvious question is, has this kind of interpretation any physical meaning or not? Well, from the quantum point of view, it's well known that quantum monodromy, as it's called, has been observed many times in many molecules. The first one is water, if I well remember. And it's seen that we see the spectrum that is different as how it should be, and the difference is just measured by the monodromy of the corresponding quantum operators. In the classical case, instead has been discovered just recently. I think, if I well remember, it was 2018, but it's something that is not really still well understood. And now we want to show another occurrence of this monodromy, which is related to what has been shown by Randall. And here we have the same system as before, but now the linear part is in resonance 1 minus 2. Okay, so what we can see is we have a singularity here which is a focus-focus singularity. So we have to go to the second derivative to investigate it. While here there is a thread of other weaker singularities, always of hyperbolic type. And the fiber over the thread here, sorry, are of this type. We called it twist tori, or they are just the covering of a circle twice. Okay. How to interpret this? Okay, here to make the joke of the parallel transport, if you like, we cannot take an elementary cell, but we take one edge which is elementary, the other one which is double, and then we play the game turning around, and here it passes exactly in the correct way, let's say. So in this case, the matrix, the monodromy matrix, is exactly the one that has been shown before by Garrett, which is 0, 1, 1/2, 1. Okay. So all these things appears naturally in interval systems. These are in dimension 2, but also in higher dimension. And another interpretation that I want to mention is that all these, let's say, phases can be interpreted as lattice defect, and has been done by some people in France, if I remember. Okay, right. So far, it was the Hamiltonian world. What does happen if we go outside the Hamiltonian world? Well, the first notion that we need is a notion of integrability. And by integrability, I mean quasi-periodic motions on tori. The motion exists, has been introduced quite recently by Bogoyavlensky, and says, assume that you have a manifold of dimension n, and then you have, say, n minus k functions that are compact and connected fibers. And then you have k, which is complementary to the number of the function vector fields, that are linearly independent and which pairwise commute, and moreover are tangent to the level set of the map F. If so, the fiber of the map F are tori of dimension k, and if there exists another vector field that has the function f1, fn minus k as first integrals, and the vector fields y1, yk as dynamical symmetry, then the flow of x is linear on tori. So this is clearly a generalization of Liouville-Arnold theorem outside the Hamiltonian setup. Okay, there are other generalizations, but this is the only one that really reduced the Hamiltonian case, if the manifold is Hamiltonian or Poisson. One can say that many, in some sense, integrals, non-holonomic systems are integral in the sense of Bogoyavlensky. And moreover, the geometry of the phase space is really the geometry of a torus bundle. And of course, we lose something. For example, if there is symmetry, integrability does not commute with the reduction, and of course, we don't have Netter theorem. And the fact that we don't have Netter theorem is really a problem, because you see, if I come back to Liouville-Arnold theorem, I just have a data set, the first integral. Okay, while on the other side, for Bogoyavlensky theorem, I need two data sets, the first integral and the symmetries. Okay, so it's really a challenge, maybe just knowing the symmetries, producing the first integral. And this is what I'm going to introduce now. To do it, we need geometry. This is the price that we have to pay to have a global Netter theorem outside the Hamiltonian setup. Okay, so we have a Lagrangian function or the configuration space, which is kinetic minus potential energy. And then I suppose that our constraint is realized by a maximal non-constant rank distribution on Q, that I call the constraint distribution. Then this HM is the Hamiltonian, this M is the image of the constraint distribution with respect to the kinetic energy metric. And this HM is the restriction of the Hamiltonian to the constraint manifold M. I can also restrict the symplectic two form to this, and it turns out that it defines a bracket which is not a Poisson bracket, but what is called an almost Poisson bracket, since Jacobi identity does not hold. Nevertheless, the dynamic can be entirely described by this bracket. And in particular, you see what is sometimes called Hamiltonian version of Noether theorem holds. A function M on R is the first integral of the dynamics if and only if it Poisson with the Hamiltonian, if commute with the Hamiltonian with respect to the almost Poisson bracket. Okay, so we have a kind of Hamiltonian formulation. Okay, kind of, because this bracket are not truly Poisson. Okay, and now introduce symmetry. If one introduces symmetry, as does in mechanics, okay, so easy things, one realizes that the infinitesimal generator of the group action does not give rise to momenta. What they gave rise more to what is called a momentum equation. Here I put equal 0, but in general here there is something different. Okay? A momentum equation which is extremely important, for example, in control theory. But now I want to look for first integral. So I introduce this distribution, which is the intersection between the constraint distribution and the tangent bundle to the group orbits. And from this, I consider a space, GS, given by the element of the Lie algebra that depends on the point on the manifold whose infinitesimal generator lies in S. So what I'm constructing here is a bundle over the configuration space of element that lies in the Lie algebra. But this space GS failed to be a Lie algebra. It's just an algebroid. But I know that point by point, they are element of the Lie algebra of the group action. So now I define what is called an horizontal gauge momentum. So I take a function on the manifold and say, if there exists a section of this bundle such that the associated momentum is the first integral of nonholonomic dynamics, well, this function is called an horizontal gauge momentum. And this section is called an horizontal symmetry. So what happens in this case is that this element that will be first integral, if I'm lucky, is not a momentum of the infinitesimal generator for the group action, but its generator, that is this element here, point by point over Q, is a linear combination of infinitesimal generators. And in particular, this J is G invariant. Okay, so now my aim is to select which section of this bundle are precisely horizontal gauge symmetry. So I need some assumption. Okay, this try origin from mathematics, but from physics, but this is essentially mathematics. So hypothesis. The first one is that the tangent bundle to the manifold is the sum of the constraint and the tangent space to the symmetry. And the other assumption is that this bundle, G, admits a global basis. In particular, this means that it is a trivial bundle. Under these two assumptions, we can write everything like this. It means element of the bundle are linear combination with functions coefficient of element of the basis. And also, in this case, the associated momentum is a linear combination of truly momenta. So now I reduced my problem of finding or looking for what are called horizontal gauge symmetry, looking for spatial functions on the configuration space. I need one more assumption. It is first, consider, say, the composition of the tangent bundle in these three spaces. Well, S is the one that we know, and H is the complement of S in D, while W is the complement of S, but in the tangent bundle to the group orbits. So it turns out that if H, this horizontal space here, is one-dimensional, which means that the group is quite big, okay, then the momentum equation becomes a system of ordinary differential equation, and the unknowns are the function Fi, which depends on only one variable. And see here, you can see there is sigma. Well, sigma is a Lie algebra valued two-form that describe the decomposition of the constraint manifold D in H and S. Okay, so under these three assumptions, plus a technical one, which is not a problem, it's extremely generic, we have that the function Jxc is the first integral, and these F1, Fk are in the k-independent solution of these systems of ordinary differential equation defined on Q mod G, which describe, in terms of the global coordinate, in this case, the momentum equation. So in particular, we have that we can construct K, which is the rank of the bundle GS, functionally independent and G invariant horizontal gauge momenta. So we have an algorithm that allows to construct first integral out of symmetry also in this case. That is outside the Hamiltonian setup. So now I don't want to enter details. I just say that if one sit down and count, can realize that if the three assumptions are satisfied, indeed the system admits K plus 1 first integral, is written here, and therefore the reduced space M mod G admits the dynamics of the reduced space is integrable, meaning that I can really write the solution. And if some compactness assumption is satisfied, it is periodic. Here I want just to show that there are systems that satisfies this theorem. So all these systems are integrable, and 1, 2, 3, and 4 are not only integrable, but the reduced dynamic is periodic, and one can reconstruct to a quasi-periodic dynamics. So what next? We have integrability. I know how to produce first integral from symmetries. My next step is the following. I consider here what we call the bottom of a bottle and a ball that rolls without lying on it. It is well known if we just consider a particle on this system, well, this system has monodromy, and its quantum counterpart has been measured in many molecules, for example, in the water one. So one of the aim that we have is to see if such system, in the case of the ball, has monodromy or not, and in any case to relate the presence of monodromy to a limit as the inertia and the ratio goes to 0. Okay, but this is something for the future. And I think, yes, thanks for your attention.